Yo. Alright, we're gonna play a little bit of Helldivers 2. My friends are having trouble, or actually one of them's having trouble with his computer working for the game. And my other buddy's at work, so we're just gonna do some farming on our own. Then I'm gonna watch some of this Veritasium videos I've been waiting for, wanting to react to these. I know everybody's talking about Venezuela, but sometimes I think people get baited into talking about what they want you to talk about, or you wind up saying the same thing everybody else is saying. What else is there to be said right now? Let's get into this.
Einstein came up with a thought experiment that showed quantum mechanics breaks one of the most sacred principles in physics, that nothing can go faster than the speed of light. Physicists assumed he was wrong. They thought that at 56, Einstein was an old man past his prime and just unable to accept the new theory of physics because it was too radical.
But 30 years later, one man stumbled across Einstein's forgotten paper when he realized something. The prediction could actually be tested. When scientists ran the experiment, they were shocked. Quantum physics really does break the universal speed limit.
We're obliged to invoke something like actions going faster than light from one place to another.
This is a video about one of the spookiest and most misunderstood experiments in all of physics. And it might even be the strongest evidence we have that we live in many worlds.
If the sun were to disappear all of a sudden, how long would it take until we noticed and were released out into space? Newton's theory says that gravity acts instantly across any distance. So if there's a change in gravity, we should feel it immediately. But Newton himself was disturbed by this. That one body may act upon another at a distance is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it.
But in 1905, Einstein realized action at a distance isn't just absurd, it leads to outright paradoxes.
Einstein had discovered that observers moving at different speeds can disagree about when events happened. Let's say you see two things happen at the same time. An observer speeding past would see it differently. To them, one of these happened first, and both points of view are equally valid. But in the case of gravity, this leads to disaster. Say you see the sun disappearing and Earth flying off at the same time, as Newton predicted. Then the other observer sees something impossible. They see the Earth flying off first, even while the sun is still there, and it should of course be pulling the Earth in. So to them, it looks like cause and effect are reversed. The only way out of this paradox is to reject the assumption we started with, so gravity can't be instant. It took Einstein 10 years to fix this issue. Himself was disturbed by this. That one body may act upon another at a distance is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it.
I know if I've
But in 1905, Einstein realized action at a distance isn't just absurd, it leads to outright paradoxes.
Einstein had discovered that observers moving at different speeds can disagree about when events happen.
Where will you strike,
Let's say you see two things happen at the same time. An observer speeding past would see it differently. To them, one of these happened first, and both points of view are equally valid. But in the case of gravity, this leads to disaster. Say you see the sun disappearing and Earth flying off at the same time, as Newton predicted. Then the other observer sees something impossible. They see the Earth flying off first, even while the sun is still there, and it should of course be pulling the Earth in. So to them, it looks like cause and effect are reversed. The only way out of this paradox is to reject the assumption we started with, so gravity can't be instant. It took Einstein 10 years to fix this issue, and in the process, he completely overhauled our understanding of gravity.
I gotta go back.
Gravity is caused by the...
Unfortunately.
Einstein was an old man past his prime and just unable to accept the new theory of physics because it was too radical.
But 30 years later, one man stumbled across Einstein's forgotten paper when he realized something. The prediction could actually be tested. When scientists ran the experiment, they were shocked. Quantum physics really does break the universal speed limit.
We're obliged to invoke something like actions going faster than light from one place to another.
This is a video about one of the spookiest and most misunderstood experiments in all of physics. And it might even be the strongest evidence we have that we live in many worlds.
If the sun were to disappear all of a sudden, how long would it take until we noticed and were released out into space? Newton's theory says that gravity acts instantly across any distance, so if there's a change in gravity, we should feel it immediately. But Newton himself was disturbed by this. That one body may act upon another at a distance is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it.
It's interesting. I would have just
In
assumed it was
1905, Einstein realized action at a distance isn't just absurd, it leads to outright paradoxes.
Einstein had discovered that observers moving at different speeds can disagree about when events happened. Let's say you see two things happen at the same time. An observer speeding past would see it differently. To them, one of these happened first, and both points of view are equally valid. But in the case of gravity, this leads to disaster. Say you see the sun disappearing and Earth flying off at the same time, as Newton predicted. Then the other observer sees something impossible. They see the Earth flying off first, even while the sun is still there, and it should of course be pulling the Earth in. So to them, it looks like cause and effect are reversed. The only way out of this paradox is to reject the assumption we started with. Gravity can't be instant. It took Einstein 10 years to fix this issue, and in the process, he completely overhauled our understanding of gravity. Gravity is caused by the bending of space-time. When there's a change in gravity, that only affects the local space-time. And then that ripple spreads out to nearby regions, which spread farther out until eventually they reach us. This theory of gravity is local because effects spread from place to place at the speed of light instead of being instant. From our frame of reference, if the sun disappeared, that ripple would take about 8 minutes to reach us. Another observer might disagree about the length of the delay, but now we all agree that the sun disappeared first.
This is why nothing can go faster than light. The delay between cause and effect ensures all observers agree on the order.
After Einstein fixed gravity, all of classical physics obeyed this important rule. But then, Einstein studied the new theory of quantum mechanics and made a terrible discovery. This is one of the most famous photographs in physics. It was taken at the 1927 Solvay conference, where the architects of the brand new quantum theory gathered to discuss it. Around 60% of the attendees would win Nobel Prizes, but Einstein thought they'd gotten something fundamentally wrong, and this was his chance to prove it. So he took to the stage with a thought experiment. Imagine you fire a single electron through a narrow slit toward a circular detection screen. Well, quantum mechanics says that this electron has some sort of wave associated with it, called a wave function, which spreads out through space as it travels. When the electron hits the screen, you detect it at a single point. Where it turns up depends on the amplitude of the wave. If the wave is very big in a particular area, the electron is more likely to turn up there. Let's say it appears here. So far, everyone was following. This is what quantum mechanics predicts. But Einstein's next question surprised them. Why doesn't the electron turn up this other spot a moment later? There's only one electron, so we can't detect it twice. But the way quantum mechanics ensures this is that when the electron was detected at the first spot, its wave function collapsed to zero everywhere else instantly. That's why the probability of finding it at the second spot is now 0. There's no longer any wave there. But Einstein asked the audience to think about what this means. The measurement here must instantly affect the wave function over here, no matter how far apart these locations are. In other words, quantum mechanics requires instant influences across distance. It violates locality. Einstein concluded his talk by saying this is an entirely peculiar mechanism of action at a distance, and that this implies to my mind a contradiction with the postulate of relativity. Einstein's argument was so simple and his talk so short that people didn't know what to make of it. One audience member said, "I feel myself in a very difficult position because I don't understand what precisely is the point which Einstein wants to make. No doubt it is my fault." That man was Niels Bohr, the most influential figure in quantum physics at the time. Bohr's institute in Copenhagen had become the hub for the new field. Dozens of young scientists like Werner Heisenberg came to learn from him. As one of his disciples remembers, Bohr had invited a number of us to his home where we sat close to him, some literally at his feet on the floor so as not to miss a word. Bohr wasn't the one who wrote the mathematical rules of quantum mechanics. Instead, he told everyone what they meant. While others were confused by the theory, Bohr offered answers. His philosophy became known as the Copenhagen interpretation of quantum mechanics.
My general understanding of the Copenhagen interpretation is You have the wave function. It describes everything that you can know about a particle or a system, and it evolves according to the Schrodinger equation, and at some point you're going to make a measurement, and at that point the wave function collapses.
I think that one bit of that you said was like, the wave function is all you can know about the particle. And I think that was like a pretty important point for Bohr.
As Bohr would put it, it's wrong to think that the task of physics is to find out how nature is.
The job of physics is just to predict measurements in the lab, which quantum mechanics does incredibly well. As for what the electron is doing when you're not looking, well, to Bohr, that question didn't even make sense to ask. The wave function tells you everything physics can or should tell you.
Einstein couldn't stand the Copenhagen interpretation. In a letter to his ally Schrodinger, he called it a tranquilizing philosophy, or religion. Einstein felt his thought experiment exposed a critical weakness in the Copenhagen interpretation. He'd shown that the way the wave function collapses is non-local, and so he reasoned maybe the wave function is the problem. Maybe it's not the best way to describe the electron after all. He may not have convinced Bohr of this during his talk, but he was determined to do it during the rest of the conference.
Physicists tell a version of the story that you will find in physics textbooks.
When I went through chemistry, we kind of covered like these
and
different models.
Physicists tell
elements
amongst ourselves that what happened was Einstein and Bohr had a great debate, and Einstein was unhappy with quantum mechanics because it was fundamentally probabilistic. He tried to show that there were conceivable experiments that he could use to get around those uncertain relations. And Bohr showed over and over and over again that he couldn't do that. And eventually, everybody agreed with Bohr.
That's Adam Becker, author of What is Real, a great book about the history of quantum mechanics. As he explained to us, Bohr may have just misunderstood the purpose of Einstein's thought experiments. We have documented evidence of this in at least one case. Einstein described a thought experiment that involved a box of photons and a mirror. Its purpose was to show the non-locality of the Copenhagen interpretation in action.
Bohr just misunderstood it, and when he recounted it to others later on, he drew a little diagram of what Einstein's thought experiment setup was, and it just didn't have the mirror in it at all. And yet this is taken as like the great victory for Bohr over Einstein, which is crazy. But history is written by the victors, right?
To understand what Einstein was arguing for, think of the relationship between Newton's gravity and general relativity. Newton's theory works well in most situations, but in that theory, gravity is a non-local force, leading to paradoxes. This was the motivation for coming up with Einstein's general relativity, which is local. Einstein believed the same logic applied to quantum mechanics. His thought experiment revealed that quantum theory is non-local, so just like with Newton's gravity, quantum mechanics must not be the final theory. There must be a local one that will replace it. And as a bonus, he thought this new theory might even unify gravity with the quantum world.
It would be hard to imagine coming to the final theory right away, and the fact that you can see paradoxes like this would make you think there's got to be more to it that we just don't have yet.
Absolutely.
But Einstein hadn't even persuaded Bohr that quantum mechanics really is non-local. So in 1935, he made one last attempt to convince the community that there was a contradiction between quantum mechanics and relativity. With the help of two younger colleagues, Boris Podolsky and Nathan Rosen, he formulated another, even more striking thought experiment that shows the non-locality of quantum mechanics. This paper is now known as the EPR paper, after its authors. Here is a simplified version of their thought experiment. Imagine a single high-energy photon suddenly becomes two particles. One of them is an electron, and to conserve total charge, the other is a positron. Since one is negative and the other is positive, they cancel out. But both electrons and positrons have a property called spin, and like electric charge, this also needs to be conserved. If the light started out with zero spin, well then the two particles together must have zero total spin as well. For example, if the direction of the electron spin is this, the positron has to have spin in the opposite direction, so that they perfectly cancel out. But the electron spin could have been this instead, or this. All of these possibilities are valid, so the rules of quantum mechanics say that the electron does all of these possible things at once until it's measured. It's not just that we don't know what the spin is, the electron really is doing everything. The only restriction is whatever the electron is doing, the positron must do the exact opposite. This also means that when the electron is measured and its state is determined, so is the positrons. This is what we mean by entanglement. The two particles' states depend on each other. But how do we measure the particles and force them to do one thing? Well, for that, we use the Stern-Gerlach equation. It's essentially a strangely shaped magnet, and it's how we measure spin. The orientation of the magnets determines what axis you're measuring the spin in. For example, if the machine is like this, and we shoot in a particle with spin in the positive z direction, it will certainly go to this spot we'll call plus. If instead, a particle has negative z spin, it will certainly go down to minus. So this Stern Gerlach machine measures spin in the z-axis. So what happens when we put in one of our entangled particles? When the electron goes into this machine, it either goes to plus or to minus, with 50-50 probability. Let's say our electron goes to plus. Well, this means it went from being in an indeterminate state to positive z spin. But what about the positron? Well, the only way to conserve spin is if it's now in the negative z spin state. When it's measured, there is a 100% chance it's minus. It has to be that way to conserve spin. But the authors of the paper realized there's something very odd about this result.
To see what's wrong with this, let's imagine that the electron and the positron carry these envelopes with them. These envelopes represent the state of the two particles. Until they're measured, both of the particles are in a superposition of being plus and minus at the same time. So both options are in the envelope.
Okay. Yeah, I understand this.
But now let's move the positron to someone who's far, far away.
Oh, I think I remember reading this.
Opening the envelope is like measuring the spin of the electron. But that causes the wave function of the electron to collapse to just one possibility. In this case, it's plus. But what happens to the other envelope far away? Well, it needs to instantly collapse to minus, because otherwise, when the experimenter opens their envelope, they have a chance of seeing plus, which would violate the conservation of spin. But if it needs to collapse instantly when the electron is measured, then how does it know what to collapse to? It must receive intel from the faraway electron. But that message has to travel much faster.
Okay, maybe I'm super naive, but I always just assume that the perception of space in between those particles isn't real, right? Like, well, it is, but they're connected on another dimension, right? So we may not see that connection, and that connection may not really make sense to like our 3D interpretation of the universe, but those things are tied together, right? But I think this is what they mean by quantum entanglement, right?
Than the speed of light to get to the positron in time. And so with this argument, Einstein, Podolsky, and Rosen had shown that the Copenhagen interpretation of quantum mechanics really is non-local. Einstein had already shown this in his conference talk, but this argument was even more decisive.
It does seem like it's the same thing, but now it's ramped up and you've got these two separate particles to do those two separate measurements, and one measurement influencing the other measurement definitely feels wrong.
Yeah, exactly. I think he really realized that it's measurements that are the problem in quantum mechanics.
The wave function of a single particle or of this pair of particles can end.
Pretty intuitive, right? That it. Maybe I'm misunderstanding this, but I don't think the issue is that would the universe be non-local or would it be local? Well, no. See, my conception of the universe is that it's kind of it's local and it's non-local at the same time. Like all of the matter is all bound together in reality. That's the way I view it. They have different degrees of influence on other pieces of matter in the universe or whatever, at different quote-unquote points in time, I suppose. Yeah, this doesn't really make any sense. But yeah, I mean, I think the way I view it is, if particles really are spread out across the entire universe, their wave function anyways, then every particle must be, I mean, of course it is, quantum entangled. We call it quantum, we think of it happening like in a different reality or different plane of existence, but it is our plane of existence. We just can't really see it. And we can't really conceive of it. Freedom never! Oh my god.
Have a taste of democracy!
Sure hope there's nothing behind me. Oh my god, please tell me I have another magazine. Ah! Never mind. Or would this be a clip? No, this would not be a clip.
Mag's empty!
I guess it would be a magazine then. Ammo cartridge? No. Alright.
End up
Anyways.
spread over vast distances. That isn't itself an issue, but when the wave function collapses, the information about that collapse needs to spread.
See, I don't know. Again, I could be just solely ignorant. Keep in mind, like, I didn't go that far into quantum mechanics or anything. I just feel like when we say the waveform is collapsing, I think we forget that the waveform is like a scientific representation of what the atom or the molecule is. I don't think the waveform is actually... Oh yeah, I like this thing. Swap this out. No, I can't. The waveform isn't really collapsing, it's that the waveform... The equation is being solved. You know, our quote-unquote uncertainty is being resolved, not the universe's uncertainty.
Spread everywhere the wave function is. That's what makes quantum mechanics non-local.
The EPR paper didn't just point out this non-locality issue. They proved that there is only one local alternative theory for explaining this experiment. In this local story, instead of the electron choosing whether to be plus or minus when it's measured,
It's both.
it actually makes that choice when it's still in contact with the positron. There's some random way that this
okay.
plus and minus gets put into these two envelopes. Which is why the plus and minus are called hidden variables. And because this alternative theory assigns these hidden variables in a local way while they're still in contact with each other,
Yeah. We
rather
just
than
don't know
over a
about
big
it.
distance,
It's just like,
we
we
call
don't know
this
what's in
a
the, in the
local
envelope.
hidden variable theory. Now, this local hidden variable theory is going to be able to explain this experiment really simply. Let's pass away the positron. And now, when the electron is measured as a plus, it doesn't have to rush to tell the positron. The
Positron was
positron
already positron.
knows. There is no action at
Or,
a
I mean, the
distance.
spin on the positron
This
is
local hidden variable story is so much more sensible than the quantum one.
So
obviously, right?
we're forced to accept one of two explanations for this experiment. Either non-locality, like the Copenhagen interpretation of quantum mechanics, or a local hidden variable theory. Given that non-local action at a distance contradicts relativity, Einstein thought this was definitive
any,
proof
like,
that the
silent
Copenhagen
weapons,
interpretation of quantum mechanics
Everything's
is
gonna
wrong,
cause a noise.
and therefore there must be some local hidden variable theory that will replace it. Einstein showed us that quantum mechanics allows influences that seem to travel faster than light. But with today's video sponsor, you can have your own spooky action at a distance. With one click, NordVPN can teleport your digital presence anywhere in the world. It's not actually faster than light, but it might feel like it. NordVPN has thousands of servers in over 120 countries, which means you can access content that would otherwise be region locked. This way, you can access all your favorite content from wherever you are with virtually no lag. But it's not just about access.
Does that count?
Every
Does
time
that take
you
out that
connect
little
to
hat?
public Wi-Fi at a coffee shop, an airport, or a hotel, you're potentially exposing your data to anyone on that network. Now, NordVPN encrypts your connection, so even if someone intercepts your traffic, all they see is gibberish. And with their strict no-logs policy, your browsing stays private. One account covers up to 10 devices, so you can protect your phone, laptop, tablet, even your router. When you use my link, you'll get a huge discount on a 2-year plan plus 4 additional bonus months. Get it at nordvpn.com/Veritasium. It's risk-free with Nord's 30-day money-back guarantee. So go check it out at nordvpn.com/Veritasium. You can scan this QR code or click that link down in the description. I want to thank NordVPN for sponsoring this part of the video. Now back
Can't
to
win them
Bell's
all.
video.
The EPR paper certainly got a lot of attention. Without asking Einstein, Podolsky leaked the paper to the press, and the story ended up in the New York Times.
Prodigious harvest of the day's intelligence is reached.
Einstein was the most famous scientist in the world.
I didn't know this
He was going after the strange
Sorry,
but
man.
successful theory of quantum mechanics. So, of course, the press loved it. But what did scientists think of the argument itself?
So the reaction of the physics community was at first mixed. There were some people, sort of old allies of Einstein's,
Oh my
We were
god!
very happy. Schrodinger being sort of at the top of that list. And in fact, in an attempt to clear up some of the misunderstandings that people were having about the EPR paper, Schrodinger publishes the thought experiment known as Schrodinger's cat, sort of back up Einstein and show the kind of problem that he and Einstein had with quantum physics. Bohr, meanwhile, was like, oh my god, what the hell is this? He must be wrong. How do we show that he's wrong? Then Bohr ultimately, in his sort of painful and complicated style, ends up coming up with a response to the EPR paper. This response is sort of famously obscure and difficult to understand, and I have read it in detail, and I will tell you, Bohr's reply is either nonsensical or makes some actual mistakes.
There's a very well-turned sentence which I believe Bohr has a bit of trouble in formulating, and whose meaning is just absolutely obscure to me.
Bohr said in his reply to EPR, in his multiple replies to EPR, that there is no question of anything non-local going on. So the ultimate reaction of the physics community, at least in the immediate years and decades following the publication of EPR and Bohr's reply in 1935, was to think that Bohr had settled it with his reply, even though people didn't really understand what Bohr had said.
2 decades later, Einstein died, still questioning quantum mechanics, but the majority of the physics community had moved on without him. Bohr, however, never forgot about the EPR paper. In 1962, 7 years after Einstein's death, Bohr gave an interview about Einstein, and he lamented that Einstein wasted decades on fruitless thought experiments because he simply could not accept quantum mechanics. It was terrible that Einstein fell in that trap to work with Podolsky, Bohr said. Rosen is worse from my point of view. Rosen even today believes the EPR thought experiment. Podolsky has given it up, as far as I know. The whole idea is absolutely nothing when one really gets into it. You may think that I say it too strongly, but it is true. There's absolutely no problem in it. The next day, Bohr took a nap after lunch and never woke up. And so, after many decades, the Einstein-Bohr debate was over.
Bohr's authority was part of the reason the EPR paper didn't get the attention it deserved.
But there was another reason physicists ignored it. In the EPR experiment, both theories, Copenhagen quantum mechanics and Einstein's local hidden variable alternative, make exactly the same prediction. You get the same results either way. Debating two different interpretations of the same experimental result seemed like armchair philosophy, not real physics. The Copenhagen interpretation makes good predictions, so why not just teach that and move on?
It just seems like, shut up and calculate, I think is the message that kind of gets pushed.
The general attitude was, this is done. Who cares? None of this matters. It's all settled. Einstein and Bohr had a big debate about it, and Bohr won. Do you think you're smarter than Niels Bohr? Do you think you're smarter than Albert Einstein?
It seemed like it would be impossible to resolve this debate until another physicist turned his attention to it.
John Bell was an undergraduate student shortly after World War II in this new era of physics, and so, of course, he was taught the Copenhagen interpretation.
John Bell's doubts about quantum mechanics, by his own recollection, showed up basically the minute he learned it. In his first quantum mechanics class, he was, getting pretty upset with the instructors and saying, you're being too vague. What the heck do you mean about measurement?
Bell was never fully satisfied by the answers he got about the foundations of quantum mechanics. But when he was doing his PhD, he was encouraged to study something a little bit more respectable. And so he studied nuclear physics and went on to have a very accomplished career at CERN. But after 8 years of working in particle physics, in 1963 he took an academic sabbatical. And finally, he had time to focus on his doubts about quantum mechanics. He said, I always knew it was waiting for me. He began by re-examining the old debates and the papers that most physicists had long since dismissed as philosophical distractions, including the EPR paper. After this research, he said, I felt that Einstein's intellectual superiority over Bohr, in this instance, was enormous, a vast gulf between the man who saw clearly what was needed and the obscurantist. He realized Einstein's logic was sound. One of the two conclusions is true.
The question was, could you prove which one using an experiment?
An experiment of this sort seemed much more feasible by Bell's time. The EPR paper was the first to consider the idea of entanglement. These days, entanglement is a core feature of quantum mechanics. but Einstein had been first to even point out entanglement existed. This is why the EPR paper was set up as a thought experiment, because no one had made such an exotic state of matter in 1935. But in the intervening decades between Einstein's work and Bell's, between 1935 and 1964, entanglement had become a serious topic of study. By Bell's time, there were reliable ways to make it in the lab. In fact, Madame Wu had famously reproduced the EPR thought experiment as a real experiment. But simply doing the EPR experiment in real life isn't enough to tell you which explanation is correct, since both predict the same thing. But Bell wondered if there was another version of the experiment where the non-local and local theories would have to give a different result.
You're asking that question, and you're playing with the EPR setup, that is like, oh, it's literally, not just figuratively, a twist, right?
Here's a simplified version of Bell's experiment. Make your entangled electron and positron again. But now, instead of just measuring them with a Stern Gerlach machine like this, the experimenters get a choice about how to orient their machine. The three different choices are 0 degrees, 120 degrees, and 240 degrees. This is the twist on the EPR experiment. The experimenters get to choose independently. So the electron might be measured at 0 degrees, while the positron is measured at 240 degrees.
Same gun or what?
If both experimenters happen to choose the same axis, then we know what happens. They have to get the opposite result as each other, to conserve spin. The interesting case is when the experimenters happen to choose different axes. The number we want to predict here is the disagreement rate, the probability that the electron's result is different from the positron's. First, let's see what quantum mechanics predicts for this number. Let's say the electron is measured with the 0 degree axis and comes out as plus. Now that its spin has collapsed to positive z, the positron spin needs to instantly collapse to be negative z. This is the non-local part of quantum mechanics. But what happens when this positron is measured by a machine tilted at 120 degrees? You can see that the positron spin is already almost facing the plus end of the machine, so it's much more likely to go to plus. In fact, there's a 75% chance it goes to plus and only a 25% chance it goes to minus. So the disagreement rate is 25%. And we can show that for any two different axes the experimenters select, the geometry is analogous. So they all have the same disagreement rate of 25%. Anytime the experimenters choose different axes, they will get the same outcome 75% of the time and different outcomes 25% of the time.
Now let's consider the local hidden variable alternative theory. The particles here are on a mission. Their aim is to make you believe that they're acting according to quantum mechanics, when really they're acting locally. Now we are anthropomorphizing, but I think it is really useful to just imagine them this way. We're trying to figure out if it's always possible for them to use a hidden variable theory to get the same experimental outcomes as Copenhagen quantum mechanics, or if in this new situation, our scheming particles won't be able to fool us. You can think of it like this. Each of the particles is going to be asked one of three possible questions, and they need to decide on their answer while they're still together, so that they can coordinate on their strategy. When they're done figuring out a plan for how they would answer any of the three questions, they pack away those hidden variables into 3 sealed envelopes for each particle. The question is, what strategy should our sneaky particles take to make people believe that they're following quantum mechanics? Remember, quantum mechanics predicted a disagreement rate of 25%, and so our particles want to match that. Whenever they happen to be asked different questions, their answer needs to disagree about 25% of the time. So, what's the best strategy? Well, there's actually only 2 things that they really can do. The first strategy is this. The electron answers the same way for each of its axes, and the positron answers in the opposite way. Let's say the electron answers with minus, and the positron with plus. But this is a terrible idea, because whatever 2 different axes the experimenters happen to choose, the disagreement rate is 100%, which is very different from 25%. And so that strategy doesn't work. But there's only one other strategy that the particles could use. Instead of the electron doing exactly the same thing for all 3 axes, it does the same thing for any 2 of its axes, and then something different for the last one. Let's just say, for example, that it does this. And then the positron does the opposite. This is just one example, but it turns out for all possible strategies like this, the disagreement rate is going to be the same. Let's imagine first that the experimenter who's measuring the electron happens to measure it in the 120-degree axis, and it gets the answer minus. They make this choice a third of the time. And now, to calculate the disagreement rate, we need to see what happens when the experimenter who's measuring the positron happens to measure a different axis from this one. So one of these two. But in either one of these cases, the positron is also minus, and so the two answers agree with each other. And so the answers have no disagreement. And so we can multiply this by 0. For 2/3 of the time, the experimenter who's measuring the electron will happen to measure it in one of the other two axes. Let's say this one. The experimenter measuring the positron will measure in one of these two axes. But you can see that they only pick an axis that disagrees half of the time. That's 1/3, which is roughly equal to 33%, which is a different number from the quantum one.
When our scheming local particles are interrogated, their answers for different questions match just a little too often. They simply can't fake the results of Copenhagen quantum mechanics.
So Vella's proof showed that non-local and local theories make different predictions about how often the two results will disagree when the experimenters measure different axes. Non-local quantum mechanics predicts disagreement only 25% of the time. Local hidden variables predicts disagreement at least 33% of the time. So to find out...
I'm gonna have to watch this video later. I'm trying to multitask.
Deploying replacement.
Just throwing away lives here.
Request approved. Reinforcements on the way.
Helldiver reporting to the front!
It's actually kind of nice not having that other video going on at the same time. Okay. Oh, do I have to be present and to be present? I didn't realize that.
Sending down support weapon.
Peace.
How'd you like to taste all freedom? Mag's empty.
Reinforcement budget running low.
These guys kill you pretty quickly.
Request approved. Reinforcements have been launched.
Oh, that doesn't even damage them.
Point me to the enemy.
Mission at 30 minutes remaining.
Probably switch.
Helldivers
That's
never
not what I
die.
do. So how do you switch firing mode? This.
Dropping a pin.
I have 1 life left too. What the heck? How many times I died? Get out of here. Ooh, flamethrower. If I do. Oh, is that or that? Okay.
Objective near your position.
Oh, I'm in that location. Peace. Jesus. Sorry guys, this is supposed to be PG-13. What these?
Request approved. Reinforcements on the way.
Democracy has landed. I do like to taste the burritos.
I hate these little jumping bastards.
Bag's empty. Freedom forever!
hell's going on here? An error. Like these specimens. Oh.
Additional reinforcement funding approved.
Can he tank that? I collect the specimens.
Fire in the hole! Injury? What injury?
What the hell is it?
Canister's empty!
Extracted the specimen. Oh, cool. Let me get the fuck out of here. Any shenanigans happen? Extraction. So only do this? Oh.
Tagging map.
Oh, great. Oh shit, I still have the case down there, huh? Honestly, I'm just gonna not use that gun, because that gun is kind of bad for myself. Okay, so. I'll extract them. Right here.
Dropping a pin.
Mission at 20 minutes remaining. Firing orbital strike.
So do have a light, huh?
Request approved. Deploying reinforcements.
Joining the fray. That's empty.
Okay, so. Flamethrower does me any good right now.
There's something here.
Yeah, I should go, but curious.
Additional reinforcement funding approved.
Oh, nice. Let's take a shot. Serious.
That's empty. That's empty. That's empty. That's called democracy. That's empty.
Oh my god. Dude's bugging out over there.
Sending down equipment package.
Back to this again. There's probably little spawn things in here, but probably destroy it.
Nothing in the chamber. That's empty. Not today!
Oh, motherfucker.
Fire in the hole! That's empty.
AIA deploying replacement. Request approved. Reinforcements have been launched.
Kill him.
Ready to liberate! For prosperity!
Other little spawn stations. I can take them. Ow, ow. I'm not able to. Or I guess that means I gotta go to the other objective. Hey, ow.
Additional reinforcements left in
Ow.
Alpha.
Ow. Look. Ow. Okay.
Mission at 10 minutes remaining.
I have a lot of time.
Bag's empty!
Democracy has landed.
I'm gonna change my voice.
That's empty. Have a taste of democracy.
You guy disappear on the ground?
Throwing grenade. How about a nice cup of liberty? Get some! Get some! Ah!
Additional reinforcement funding approved.
Jesus, dude.
Freedom never serves! I need stabs!
Another KIA
Damn
deployment
it.
placement. Request approved. Reinforcements on the way.
Reporting to the front.
Five minutes left. We can't stay this low much longer, Helldiver. Firing orbital strike.
For prosperity! Can't liberate with this.
Additional reinforcement funding approved.
traitor!
Damn it. Stop. The hell are they spawning out? You destroy this shit. Annoying as fuck. Okay, I got that one. Peace. What is this? Oh god. Oh god, I don't have time for this bullshit. That's great.
Mag's empty. Throwing grenade. Say hello to democracy!
Extraction shuttle deployed. Bravely they delved beyond liberty's light, never to return.
Alright. Well, that's probably gonna be it for now. That was something. It's a fun game, but I think it's definitely a lot better when you have some teammates. We'll get that going though.
Helldivers outside extraction radius. Pelican 1 aborting pickup.
Okay, let's see what we got here. Did I get anything for that? No, not really. Alright, well, that's alright. That's good enough for now. Catch you guys later.